Hey there. We saw in the previous section how to find the slope or the derivative of a function at a particular value. In the very last example in 3.1, I changed it up a little bit and we replaced that particular value of x with x itself. So that instead of finding a particular slope at a particular point, we found a slope function, and then we're able to evaluate it at several values if we wanted. So that's the only real change at the first part of this section 3.2 is we're replacing the a in the previous section with x's. Okay, and what this will do is it'll build us a function of x. Okay, so we can think of it as a slope function for your original function. If this limit exists, we say that the function's differentiable at a particular value, and then we can just evaluate our new function at these particular values. So we can find the slope at several points rather than having to redo the limit problem every time we want to find slope. We are going to eventually hit a wall with limits. There's only so much you can do algebraically with them before it becomes not even unbearable, but impossible. So we will segue into some so-called shortcuts for derivatives. But I think it's important to understand where this comes from, that this is a construct of limits, and anytime we build something new in calculus, we will revert back to limits. So let's just look at a few more examples involving limits and finding a derivative or a slope function for another function. So this first example, we're looking at f of x equals x cubed. So we've seen a few quadratics. This will just have a little more going on, but it'll be very similar to any other polynomial. So f prime of x is going to be the limit as h approaches 0 of f of x plus h, so x plus h cubed, minus f of x, which is just our original, over h. So that's just applying the definition. Now note, based on how this definition is set up, we have a limit as h approaches 0 and h is in the denominator. We're never going to be able to evaluate this on the first step. So you're always going to go after the numerator. And hopefully an h will pop out and we can reduce the fraction and get rid of this indeterminate form. So let's multiply everything out on top. We have make sure you're writing the limit on each step, or else you'll have h's in your answers. So we have the limit as h approaches 0. On top, if I cube that, we get x cubed plus 3x squared h plus 3x h squared plus h cubed minus the x cubed. So hopefully you see that the x cubes will drop out, and now everything left on top has an h on it, so we can factor that h out. So we have the limit as h approaches 0 of, if I pull that h out, we have 3x squared plus 3xh plus h squared on top, and then the h on the bottom. And you can see what we wanted to have happen does happen. Those h's drop out. We reduce the fraction. We have the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And now the easiest part of the problem is actually doing the calculus, the limit part. So as h approaches 0, there's an h here and a here, so both of these terms approach 0. And so what are we left with? 3x squared is constant with respect to h, and so we just get that. So the derivative of x cubed is 3x squared. This is the slope of x cubed at any value. So if we wanted the slope at x equals, say, 2, that would be f prime of 2. So in the previous section, we computed f prime of 2 directly, but if I then wanted, the slope at another value, we'd have to do another limit problem. So the benefit of building this general function is I can just plug things in now. So if I plug 2 into the derivative, we get 3 times 2 squared, or 12. And if I plug -1 in, we get 3 times -1 squared, or 3. Okay, so it's unfortunate, but quite often the way it works in a math book is you have some function, you plug a number in, and you move on to the next problem. New function, new number to plug in, but that's not how we use functions in mathematics. When we're doing applications, if perhaps this original function was the position of a particle, the derivative would be how fast it's traveling, and I'd probably want to know how fast it's going at lots of values. This is where spreadsheets and things like that get all their business, is I can enter the function x cubed, I can enter the function 3x squared, and I can have a spreadsheet plug in tens of thousands of values if needed. Okay, so that's the benefit of getting this general form. So this is the slope function. Because I've got real number outputs, when I plugged in 2 and -1, you would say this function's differentiable at those values. Okay, so not too much different from the previous section, except we have x's and h's. So you just have to pay attention and be careful. Let's look at this next one here. These are usually the worst, or at least initially. Anything with ratios where the variable shows up on the top and the bottom, these are usually the nastiest. So if you can handle this one, we're in good shape. So again, the definition does not change. It is going to be a limit as h approaches 0. Now we have to evaluate x at x plus h. So this would be 4 times x plus h over x plus h plus 1. So that's g of x plus h minus g of x, which is your original function. So far it looks bad, but don't forget we also have that h in the bottom. So what's messy about these is we have what you referred to in algebra courses as complex fractions, meaning fractions within fractions. So there's a pretty simple approach here to make things better, and it's going to be to multiply by the least common denominator of the two fractions on top. So we go after it as if we were adding those two fractions. And the least common denominator here, since one has an h and one doesn't, they're never going to have any common terms. So we're going to multiply by that product. So we have x plus h plus 1 times x plus 1. And if I distributed that on top, fractions would go away. Well, we can't just multiply by whatever we want unless it's equal to 1. So the approach here is to multiply top and bottom by the least common denominator. And you have to remember we're going to distribute. So we multiply everything by it on top. And if I do that, we have the limit as h approaches 0. When I multiply the first term, the x plus h plus 1 term cancels out, and I'm left with 4x plus h, and then the x plus 1. Minus, if I multiply the second term, this part, the x plus 1's drop out, and I have 4x times x plus h plus 1. Don't forget the denominator. We have the h, and then we also have that least common denominator from the previous step. Don't multiply this stuff out. Remember, we want that h sitting there. Now the problem sort of looks like example 1. I mean, there's more going on, but it looks like we have a single fraction now, and it looks like just the usual algebra on top. Multiply everything out and then just kind of see where it takes us. So we'll have the limit as h approaches 0. If I multiply everything out on top, I get 4x squared. So we're going to FOIL these two terms out and the first two terms and then multiply through by 4. And that'll give us 4x squared plus 4xh plus 4x plus 4h minus, and then we also have to distribute the negative 4x to the second term. So we'll have negative 4x squared minus 4xh minus 4x. All of this will be over h times x plus h plus 1 times x plus 1. So leave the denominator alone. We want that h staring at us. So what are we hoping for? Well, we're hoping all the terms without h's go away. So if we look closely here, we see 4x squared minus 4x squared. We see 4x minus 4x. There's even an additional cancellation. We have 4xh minus 4xh. So a bunch of stuff goes away. That's what I mean about these ones with ratios getting bad before they get better. So this becomes the limit as h approaches 0 of on top, and I think it's good to include this step. Don't try to cancel it too much at once, or you might end up crossing everything out. We have x plus 1. So now you can see that the h's drop. So we have the limit as h approaches 0 of 4 over x plus h plus 1 times x plus 1. And now for the calculus part. Everything we've done now, except for using a calculus definition, has been algebra. As h goes to 0, that little h goes away. And we get left with 4 over x plus 1 quantity squared. So this is the slope of g of x at any x not equal to negative 1. So if you look back at the original function, its domain excludes negative 1 because we can't divide by 0. But anything else I can plug in and I'll get a functional value from the original and a slope from this. So this is our g prime of x. Okay, so that's our slope function. Let's do one more of these before we move on and kind of talk about when a function, so this function here doesn't have a derivative at negative 1. So domain could be an issue. Domain's also tied to continuity. So that's where continuity is going to come up again. So we want to know what functions are and are not differentiable. So we'll get to that on the next page. But let's do one more limit problem. And for this one, I'm just going to call this f of x so you can think about your function notation for your definition. So f prime of x is going to be the limit as h approaches 0. We're going to evaluate this at x plus h. So we get x plus h plus the square root of x plus h minus x plus the square root of x. So that's f of x plus h minus f of x over h. So this one looks a little bit tricky. We have learned some techniques for how to deal with limits involving roots, and you know that the conjugate is coming up somewhere. What I'm going to do is group things. Some of this has radical stuff and some does not. So what I'm going to do is I'm going to group the radical stuff, and getting carried away with colors here. It's like having a box of crayons. And I'm going to group the non-radical stuff together. And I'm going to rip this fraction apart. So what this gives us is a limit as h goes to 0 of the green part, the part that does not have the radical, x plus h minus x over h, plus the limit as h approaches 0 of the purple part, the part that does have radicals, x plus h minus root x over h. So what I'm doing here is I'm doing the sum law for limits. Okay, so we're breaking, I'm regrouping or grouping things a particular way, and then I'm ripping the fraction apart and breaking it into two limit problems. One of them is easier than the other. Certainly the first one, the x's drop away. We have h over h, which is just 1, so this part's 1. So we're done with the first one. And if you look back at the original function, which is sort of crossed out now, you can see that the first part of your original function is the function y equals x, and that's linear and its slope is 1. So we should have gotten 1 for that part. For the other part, you know that we're going to multiply by conjugates. So we're going to multiply by square root of x plus h plus the square root of x over h. Let's fix that. We're multiplying by that over itself. So we're multiplying by conjugate, top and bottom. We don't switch the sign under the radical, we switch the sign between terms. Okay, so let's see where that takes us. We still have a limit to do. The first part's just part of the answer. So we have the limit, if I multiply here on top, we're squaring the radical, so we get x plus h. No middle term because they are conjugates, and then we have a minus x over h times, and just like before, don't simplify the bottom, leave it alone. We want that h sitting there. If I multiplied the h through, I'd have to turn right back around and factor it out. So kind of like the fraction problem on the previous example 2, these usually get worse before they get better. But it only takes a step or two to kind of clean things up, and it's all the usual algebra you've been doing over the years. The x's drop out, and so we have 1 plus the limit. After the x's drop out, the h reduces. H divided by h is 1, and we end up here with that sum of the roots on the bottom. And now we can take the limit. The limit as h goes to 0, that little h goes away, and we're left with 1 plus 1 over 2 root x. So this is my f prime of x. Or you could write y prime. Y prime is used as well. Not as much in this course, but I'm going to throw in as much notation at you as I can in your first calculus course so that it doesn't bother you as you kind of move through the sequence. So this is the slope of y equals x plus the square root of x. And this is for x strictly greater than 0. Now you might think greater than or equal to because the original function, the domain is everything bigger than or equal to 0. The problem now is we have a root in the denominator. So we can't plug 0 anymore. So we only get the slope for positive values. You might want to look at the graph of x plus root x to see why that might be the case. I think what you'll see is at x equals 0, we would have what looks like a vertical tangent. And you know the slope of a vertical line is undefined. So this is leading us to when is a function differentiable. And there are basically three things to look out for here, and I'm going to look at those graphically in the next example. So I will see you on page 6.